Welcome to my tutorial on how to solve X-bar and C-chart problems. It's a big part of quality management is actually being able to create and then use these charts. And honestly, the biggest challenge with them is setting up your upper and lower control limits. So there's some calculations involved. I'll show you the formulas and we'll run through just two examples. I'm going to cover mean charts and range charts, or what we call X-bar charts and R charts in this tutorial because these two actually should work together. So I gave an example during the lecture about checking the temperature of coffee and taking 10 samples of cups of coffee, so your N equals 10, and then checking the temperature on those 10, and then you average those together. That gives you your sample mean. That's what you put on your control chart. Pretty simple. But that's just the mean of the sample of 10 cups of coffee. So think about this is where range charts come into play. So your mean might be perfectly 200 degrees, which is our target for an espresso. And the mean might be there, but think about that. Across those 10 cups, there could be one that's 100 degrees, which is way too cold for coffee or espresso, and one could be 400 degrees, which is way too high for espresso, but the mean would collapse those to the middle. And so the mean wouldn't reveal that the difference between your hottest cup and your coldest cup, which is the range, is way too wide. And so, if you just looked at the range, then your mean might be wrong. So you really need to look at both of these together. So it's just great to kind of hit them at the same time. So these type of charts work when it's a variable. So it's something you can measure like temperature, weight, volume, height, depth, anything like that. So you can actually put a real number on it. That's different from charts where we're just going to count something and say, how many failures were there of 10? That would be a P chart and potentially a C chart. So we'll talk about those separately. But these are really kind of the most popular charts that are used in Six Sigma quality control. So we still take a sample, and that sample will have a size, and it'll be a set size, and let's say it's 10 or 5 or 20 or whatever it is, and that would be N. N is equal to the number of observations in your sample. And you could take 12 samples a day, so you could do it every hour for a 12-hour shift, but your N would still be the number of cups of coffee in each sample, not the number of samples. So be careful that people get tripped up on that. And we'll still use an upper and lower control limit, and but how we calculate them differs between X bar and R charts. And this is our goal, is to find this chart and be able to actually put a number on that upper control limit and that lower control limit, because once you do that, it's done. And then you just take your sample tomorrow, the next day, the following 2 weeks, 6 weeks, 6 months from now, 2 years from now. You calculate that sample mean or that sample range, and you post it on the chart. Getting the UCL and LCL correct is the challenge. So here's the formula to do that. I'm going to give them to you one at a time. So this is what's known as the method to calculate the UCL and the LCL when you don't know S. S is the standard deviation of the process. There's a different method. I'll show you that at the very end if you know it. But you'll recognize problems that want you to solve it this way, but because it'll say in the problem, use the chart. And I'll show you the chart in just a minute. The R chart, upper and lower control limits, you can see, I'll try to use my pen device here. Get down to where it is. There we go. See, is it going to come up in there? Nope, not going to let me write on it. That's okay. You can see that value in there, D4 and D3 in the top equation, and then down at the bottom equation there's this A2 value. Well, those all come from this magical chart that's talked about in the text, and it's a statistics chart. Here it is. It's available in the back of every operations management text ever written. It's available on the internet. It's a standard statistical table, just like the Z table and the T tables and things that you've used previously in statistics. This is a table that's specifically designed to calculate UCLs and LCLs. And you notice on this one I marked it. It's a 3 sigma chart. And you should recognize that from your statistics, because we often say 2 sigma is a 95% confidence, 3 sigma is a 99.7% confidence. So that's where that comes from. It'll always tell you in the problem, or should always tell you in the problem, which chart to use, or it'll provide the chart so you don't have to worry about it. But there is a difference between the charts whether you choose one or the other. So we're going to try out these formulas. Here's the problem. The filling process for Energy Bust puts 250 milliliters, very small amount, of their secret formula in each bottle. The average range of recent samples, n equals 6, is 10 milliliters. So we know what that central range is. We've taken several samples over time. Usually the magic number is 20. So we took 20 samples of 6, and we found that the range is normally, if I can use that term, 10 milliliters. So keep that in mind. Help Energy Bust identify the UCL and LCL for their range and X-bar charts based on a 3 sigma, there it is, 99.7% confidence. The mean of the process is 250 milliliters. So we already know some key pieces of this formula. So if we look at it, we see the D4 is going to be a value off this table. R bar is the average range. Well, we were just told that was 10. So we're just going to substitute in 10 and multiply it times D4. That's going to give us our upper. And we're going to take D3 and multiply it by 10 to get our lower control limit. Now the table over here, please read these very carefully. This is asking for sample size. So when we look at our sample size, it says n equals 6. So I'm going to go to the row that says 6, and we're going to use these values to calculate our upper and lower control limits. And you can see I already brought the equation in for the X-bar chart, and you see it says UCL of X-bar. That's the upper control limit for an X-bar chart. This is the upper control limit for an R chart. Very easy to follow these. And we're just going to take the mean of the process plus A2, value right off the table, times R bar, which we know is 10. So these mathematically, it's really simple algebra to put these together. So I see up on the table, there's my D3 value. There's my D4 value. So now I'm ready to plug those into the equation. And I get my upper control limit for R is 2.004 times 10, so do the math on a calculator really quick. So my upper control limit is going to be 20.04. My lower control limit, if I go over here to the table, the value is 0. So it's going to be 0 times 10, which still comes out to 0 in anybody's math. So I have my upper and lower control limits for my R chart. Now it's not an R bar chart, it's just saying we use the average range, and that was from right up here, 10 milliliters. Let's quick go down and take a look at our UCL for the X bar chart. So X double bar, that means what is the grand mean? It means what is the mean of a whole bunch, usually 20 samples. And that comes from right up here in the first sentence. It says Energy Bust puts 250 milliliters in their formula. So we're going to use that 250 plus A2, figure off the table, A2 right down there, 0.483, excuse me, times our average range, which was 10, and that tells us that our upper control limit is 254, and we're going to use minus to get to the lower, so the mean minus 0.483 times 10 is going to be 245. So I hope, even though we haven't put it on the chart yet, we're about to, you're already picturing in your mind, I got my upper control limit is 254, my lower is 245, so when I take my samples and I calculate the mean, it better be somewhere in between those two, or my process is out of control and I have to go investigate. If it's within those, we say our process is in control, and unless we see a pattern in those means that it's about to go out of control, we let the process keep running. So let's see what it looks like on the charts. Here's our range chart. Our two values come in, and we also know that the average range is 10, so we could have put 10 there in that mean line. I just didn't bother because it doesn't matter that much where the mean is. We just want to make sure that the samples fall within that upper and lower control limit. Then we got our X-bar chart. 254.83 and 245.17. And now we write these down, we draw them on our whiteboard over top the machine, we post it on a poster, however we do it, and then as we take samples, we just check them against this chart. Put a dot on the chart, put a dot on the chart, put a dot on the chart, and see if there suddenly starts to become a trend in those dots. That means we're in trouble. Or if one of our dots falls outside of the upper and lower, we're in trouble. All right, not so bad. I hope that helped. Put your mind around it as well as the math. Now, there's a second thing I'm calling the special case, which really isn't that special. But there are cases when we know the standard deviation of the process, and it'll actually say that in the problem. It'll say the mean of the process is this, and the standard deviation of the process is, etc. So sometimes that's given, and in that case, you don't need to use that crazy stats table. You can just calculate the upper and lower control limits, but the formula changes. So when you see the problem, take a look and see if it tells you to use the chart, or see if it tells you, oh, the standard deviation is known. If that's the case, this is the formula you use. And it's still, this is for the X bar chart, it's still that same idea that we're going to use the what's called grand mean, or the X double bar, which tells us that we have at least 20 examples and we have a good prediction of what the mean of the process is. We'd use that. Now Z comes from statistics. That comes right off the Z table. But there's a cheat way. You don't have to actually go look this up on a Z table, because we know when the problem says you need to have either 2 sigma or 95% confidence or a 5% type 1 error. So anytime those things add up to 100, either Z of 2 or 95 or 5%, we know that Z will be, sometimes people in the field like me just will use 2, but the real number is 1.96. And you just multiply it times. Now look at this. This sigma is the standard deviation of the sample. Well, we only had the standard deviation of the process, so we have to convert it. So watch that step. It's not a hard conversion. You take the process standard deviation and you divide it by the square root of n. So this value right here is actually the standard deviation divided by the square root. You got to make that conversion. And then the LCL is just the mean minus it. So I think I have an example here. Let's see. We got that. We got the Z. We got the standard deviation. And then here's my cheat sheet. Z of 95% or a 5% error rate is 1.96. Z of 99.7% or effectively 0 error rate is 3. So when you see the problem, it's going to be one of those two. So here's our example. Krusty Savings Bank is concerned about customer service times at the drive-up window. They want to monitor the process quality using an X bar chart. What a great idea. The process mean is 6 minutes. So now we know X double bar is 6. The standard deviation of the process is 1.5. So now we know sigma is 1.5. Sample size is 6, so n equals 6. So if I was doing this problem, I'd be writing all these down. N equals 6, sigma equals 1.5, x double bar equals 6. Develop an X bar chart that has a type 1 error of 5%. That means 95% confidence. That means we're going to use the 1.96. Recent sample means were 7.1 and 4.5 minutes. Is the process in control? So after we develop our X bar chart, we're going to check these two values and see if they're within the upper and lower control limits. So here goes. Here's our formula that I showed you earlier. The upper control limit is the mean that we had of 6 minutes plus Z, which we know is 1.96, times, and I went ahead and substituted this in, the standard deviation of the process, which is 1.5, divided by the square root of n, which is 6. And so our upper control limit is 7.20. Our lower control limit, the equation's the same except for that minus sign. So the mean is in the middle, and we're going to go plus up to the upper control limit, and we're going to go minus down to the lower control limit. So we want our values to be between 7.2 and 4.8. You really don't need the chart because I know that now I know the top and the bottom values, but since we know them, it's nice. We'll put it in there. And then we'll post that first sample. Looks good to me. It's a little high, but it's within the control limits and we don't see a pattern at this point, so we're going to let it go. Then we get our second sample and it's like, whoa, that's below the lower control limit. Now I got to go out and investigate. So the term we would use is our process is not in control and there is assignable variation, which means since it's so far out of bounds, that means that there's a cause. So is the person that's working the teller window not trained properly? Did their machine break? Was there something wrong? And actually, this one's is she's actually faster. He or she is actually faster than they should be. So why is that the case? Could we improve our means? So we would investigate to see what's going on that something's falling outside of our predicted range.